In the last video, we provided this rather contrived thought experiment to explain why the Bode stability criterion establishes an upper limit on the stability of a feedback control loop. That thought experiment may not be very satisfying for you, because it involved this rather unrealistic situation where our set point was varying sinusoidally, and we had to disconnect the feedback control loop to establish the sustained oscillations in the measured variable. However, if this were a course in signal processing, we would have already introduced the idea that any bounded signal can be represented by the sum of sine and cosine functions, known as the Fourier Transform. This is the principle of Fourier analysis, whereby a signal is decomposed into a sum of sine and cosine functions with different frequencies. Because all real signals are bounded, and all bounded signals can be represented by sums of sine and cosine functions, or sine functions and phase-shifted sine functions, then these real signals contain contributions from sine functions of many different frequencies. Furthermore, it doesn't matter whether the input comes in as a set point or it comes in as a disturbance, because the feedback control loop is a loop. So no matter where it comes in, it gets multiplied by all of the transfer functions in the open loop transfer function. The point is that any real signal coming into our feedback control loop, whether it's a set point change or a disturbance, may contain a component of that signal represented by a sine function that has the critical frequency. And it doesn't matter what happens to all of the other components. If the amplitude ratio at the critical frequency is greater than 1, then it doesn't matter what happens to all of the other sine components of that real signal. The component representing the sine function at the critical frequency will get amplified by the open loop transfer function representing the feedback control loop. And that amplification will make the process unstable when the amplitude ratio is greater than 1 at the critical frequency. So the Bode stability criterion is established because all real signals may contain a component at the critical frequency, and if the amplitude ratio is greater than 1 at that critical frequency, then the feedback control loop will amplify that component of any real signal in the process and make the process unstable. Now let's move on to consider how the Bode stability criterion can be used to analyze the stability of a process containing a time delay. In this case, we'll assume that the process obeys an FOPTD model and that the valve, measurement, and controller are represented by gains. The critical frequency for this open loop transfer function occurs at 1.69 radians per minute, and if we set the controller gain equal to 1, then the amplitude ratio of the open loop transfer function at that critical frequency is equal to 0.235. So when the controller gain is equal to 1, this process is stable. Now we could find the upper stability limit by trial and error, selecting different values for the Kc to find out when the gain crossover frequency is equal to the critical frequency of 0.169. But increasing Kc only causes the amplitude ratio to increase proportionately. That is, if we double Kc, then the amplitude ratio will also be doubled for all values of the frequency. And if we multiply Kc by 10, the amplitude ratio will be multiplied by 10 for all values of the frequency. Therefore, we can find the upper bound on Kc, or the ultimate gain, directly. We know that we have to multiply the gain at the critical frequency by 1 over 0.235. That is, 1 over the amplitude ratio at the critical frequency when our Kc is equal to 1, in order to obtain an amplitude ratio of 1. So, since we plotted the Bode diagram with the controller gain set equal to 1, we can find the ultimate gain by taking 1 over the amplitude ratio at the critical frequency, or 1 over 0.235. In this case, we get 4.25. In general, then, the ultimate gain can be found for any open loop transfer function by preparing the Bode diagram with the controller gain set equal to 1, finding the amplitude ratio at the critical frequency, and then Kcu is equal to 1 over the amplitude ratio at the critical frequency. This method works whether our initial guess for the controller gain set equal to 1 is greater than or less than the ultimate gain. This principle is used to develop what we call the gain margin. The gain margin is one measure of the stability of a feedback control loop. We'll discuss the gain margin and another value called the phase margin in the next video.